This video I'm going to prove an interesting fact. If N and M are both normal subgroups of G, then this quotient group is congruent to that quotient group. Now when I look at a statement like this, I remember the following, that if I can show a homomorphism from N to NM mod M, and then let's call the homomorphism phi, and then I can show that in this case, if I can show that the kernel of the mapping phi is N intercept N, then what we have is N mod N intercept M is isomorphic to the right side. So I'm not sure why the color changed on my board, but that's how we're going to proceed with this proof. Okay, so how about we get into it? Step 1. We'll show a homomorphism from N to NM mod M. Okay, I'm gonna have, that's gonna be necessary for me to show that these are isomorphic. Number 2, we'll show a homomorphism phi. Okay, so we will show that the kernel of phi is in fact N intercept M. And step 3 is simple. We'll conclude that N mod N intercept M is in fact isomorphic to NM mod N. Okay, so before we can show a homomorphism from N to this set, let's see what that set really is. N mod M, NM mod M is the set of capital M times, I'll call it NM, where N is in N and M is in M. Okay, but now, since both of those are M and N are both normal subgroups, this is the same as, say, M times here, M prime N. Okay, that is NM is equal to M prime N. You're not always going to get that NM is MN, even if both N and M are normal. Okay, such that blah blah blah. M is in M and N is in N. But M is in M. That means what we really have is Mn, such that N is in N. This is what this set equals. Okay? It's the set of right cosets of M, where N comes from N. Okay, so now let's define a homomorphism from N, the simpler set, to NM mod M. And we'll define phi of little n to equal, well, it's something in here. How about we let it be M times that same N? Nice and simple. N may contain N1 and N2 and N3 up to, say, N20. I can say that phi of M7 is equal to subgroup M times N20. Well, let me not, N20. But there's no reason to do that. Let's make it simple. Just let it be that. That is, whatever I put in between these brackets, it has to be in capital N, is going to equal to M times that same element. Nice, simple mapping. Okay. Alright, so now, we have to show this is a homomorphism. Okay, so phi of, say, N1, N2. Let N1 and N2 be in N. Well, by definition, this is M times N1, M2. But M is the same as MM times N1, N2. Now, I can bracket that up, and since this is since M is a normal subgroup, that's the same as the subgroup M1 times M times N2, but that's the same as just using the dissociative law. It's the same as this. But this here is just phi of N1 times phi of N2. So phi is a homomorphism from N to NM mod M. Okay, so we did step 1. We'll show that phi is a homomorphism from N to that quotient group. Now we need to show that the kernel of N is just N intersect M. So, what is the kernel of the mapping phi? Well, phi goes into here. And what's in there, what's in here, is nothing more than M times little n. And N is a subgroup. The identity is going to be ME. What is the kernel of phi? Okay. Suppose X is in the kernel of phi. On one hand, phi of X is equal to mx. On the other hand, it is equal to me. Okay, now, by definition of this quotient group, it equals this. M times something, where that something is in N. Okay, but now, this here equals M. Well, the only way a right coset of M is equal to M is if X is in M. But X is also in N. If you want to say why, because phi is a mapping from N to somewhere else. Because phi is a mapping from N to somewhere else. Don't really care what the somewhere else is. That is, phi takes things from N. Okay, so here we go. X is in M, X is in N, and X was in the kernel. But that implies that X is in N intersect N. Okay. So what we showed is that if x is in the kernel, then x is in here. That implies that everything in the kernel is in n intersect m. Now we need to do it the reverse way. Let x be in n intersect. I know I said that. N intersect m. So let x be in n intersect n, and we have to show that it is in the kernel. Now, phi of x is mx. Since x is in n intersect m, that implies that x is in m. But that implies that mx, this here, is equal to m, or me. That is, phi of x is equal to me, which implies that x is, in fact, in the kernel of phi. So we started off with x being in here, and we concluded that x is in there. Let's call this statement double star. But over here, we showed the containment the other way. Let's call that star, not triple star. By star and double star, we have that the kernel of phi is in fact equal to n intersect m. Now, we know that there's a mapping from n to NnM mod m. There's a mapping, a homomorphic mapping between those two sets. Now, if you mod, say, n by its kernel, there's a theorem that I proved that said that those two sets are now isomorphic, and that completes the proof. I'll just write that a little bit more horizontally. If you like watching proofs like this, you should seriously consider subscribing to my channel. Please leave a comment. Tell your friends, family, and enemies about my channel. See you guys in the next video. Keep watching and learning.